Welcome, everyone. In this lesson, we're going to continue on with optimization, but now we're going to get into really applied optimization problems, and we're going to see our first example with this. So we're going to be using all those techniques we've been developing, finding the critical numbers, all of our tests to figure out what's going on at the critical number. Is it a minimum or a maximum? But now we're going to kind of put it in an applied setting. And so for this first example, we're going to kind of start off easy, relatively speaking. And in this example, what we want to do is we want to plant a rectangular garden. And we're going to do this along one side of our house, and we're going to fence in the other three sides. Okay. So that's kind of the situation here. Now, the problem that we're going to actually investigate is we're going to find the dimensions of the largest garden that we can enclose using 40 feet of fencing. So this is the actual problem that we want to solve. So as soon as we see wording like largest or smallest or maximum or minimum, we're talking about an optimization problem. So the key word here is this largest. All right, so let's kind of unravel what's going on. And a good way to kind of start with these, especially when there's kind of a physical description, is to draw a diagram. So before we actually get to any calculus or really even any math, let's draw a picture of what's going on. So that's where I would start this. We're going to draw a diagram, just to kind of help us see, well, what's really going on here. All right, so we're building a rectangular garden. So let's go through the kind of the geometric description of what's happening. We're building a rectangular garden. So let's draw a rectangle. All right, there it is. There's our nice garden. And one side of this garden is going to be built alongside of a house. So it doesn't matter which, but let's just suppose that our house is over on this side. So here's our house. All right. So we're building our garden right alongside the house here. And what we're going to do is we're going to fence in the three other sides of our garden. So the sides of our garden that are going to get a fence are going to be this side right here. We're going to need a fence for that side. We're going to need a fence for this side. And then we're going to need a fence for this side over here. And the one side we're not going to need a fence for is the side that's along our house. Okay. So, no fence for this side over here. The house is kind of already doing that for us. All right, so what do we, once we have the diagram, we want to introduce some variables just to kind of help us out. And so when we talk about a rectangle, there's really kind of two dimensions to a rectangle. There's the length and the width. So it doesn't matter which. Let's just give them a name. So let's call the length of this side, we'll call this X. And we'll call the length of the other side here, we'll call it Y. And rectangles, opposite sides, have the same length. So if this side is Y over here, then that means this side also has length Y. And then similarly, if this is length X, then the opposite side also has length X. So let's just label all of our sides. Okay. So draw a diagram. It's a good place to get started. Just to have a little picture of what's going on, especially for these physical problems where there's actually something getting built. All right, so what is the question that we're trying to answer here? We're going to go back to our picture in just a second. But what is the question that we're trying to answer? Well, there's kind of two things. We want to kind of build or construct the largest garden possible. And so the question is, how do we measure the size of a garden? So our garden, if we go back up to our little diagram here, our garden is it's the amount of space. So it's the amount of space right in here. And the question is, how do we measure that space? Well, the way we do that in 2 dimensions, this is a 2-dimensional rectangle here. The way we kind of measure that is with area. So we're trying to find the largest garden. Really what we're asking for here is the area. We want to find the largest area. We want to find the garden that has the largest area. Now, if we didn't have any kind of additional information, which we're going to get to, then we could just make the garden as big as we want. But it turns out we can't. So there's a bit of a restriction here. And our restriction is that we only have 40 feet of fencing here. So we're limited. This provides us with some limit to, what our dimensions can be. So this is a limit. So we're limited by the amount of material here. Okay. So to start answering this question, the way to get started is kind of step 0 is we need to figure out what the objective and constraint equations are. So like that example we looked at in class, we're kind of given what the objective and what the constraint equations are. Now we're going to actually have to kind of figure out what they are based on the information that we're given. So we want to determine our objective and constraint equations. All right. So let's start with our objective. So our objective function. What is our objective function? Well, the objective function, this is the thing that we want to optimize. This is the thing that we either want to find the maximum of or the minimum of. So if we go back to our wording here, we want to find the largest garden. So it's that largest. We're trying to find a maximum here. And the quantity that we're trying to maximize is the area. So again, the objective equation, this is what we want to maximize or minimize. So what we want to optimize here. And in this problem, it's the area. All right, so we want to figure out, well, what's the area of our rectangle? And so if we go back up to our diagram, the area of a rectangle is just the product of the 2 dimensions. So in this case, the area is x times y. So it's the length times the width here. That's the area. It gives us a way to measure the size of our garden, the amount of kind of planting space there. All right, so that's going to be our objective. That's our objective. We're trying to maximize that function. So we'll just kind of shorten this up. We'll call this function a for area, and we'll just shorten this up to x times y. A is equal to x times y. That's going to be our area formula. All right, so then we also want to figure out the constraint equation. So our constraint equation, this is the kind of the information that we're given that kind of puts some restriction on what x and y can be. And in this case, it's the amount of material. So we can't just make this garden as big as we want because we only have, a finite amount of fencing to use. So that gives us some restriction. That puts some limit on what we can do. So it constrains us. So our constraint equation is really the amount of fencing. All right, so let's actually see how we're going to figure this out. So we want a formula. We want an equation for the amount of fencing. And we know that we only have 40 feet of fencing to use. So how do we actually measure how much fence our garden requires? And that's what we're going to put over here. So let's figure that out. So let's go back up to our diagram. And when we're looking at this, the amount of fencing well, only 3 sides of this rectangle are going to get a fence. So this side is going to get a fence. And so if y is measuring the length, we're going to need y feet of fencing for that side. So the amount of fence for this side will be y. Then the amount of fence that we'll need for this other side, that'll be length x, because that's the length of that other side. So we're going to add that together. And then finally, we need fencing for this other side, which has length y. So we're going to need a fence for that side. And so if we combine like terms, what we're seeing here is that the amount of fencing that we're going to need is x plus 2y. Now, as a bit of contrast here, when we talk about rectangles, really the area is one common formula, but another common formula is the perimeter. So the amount of fencing here is kind of related to the perimeter, except we're excluding one of the sides, the side that we don't need the fencing for. So the perimeter of a rectangle is just 2x plus 2y. And so what you're doing with perimeter is you're just adding up all the lengths here. But for the amount of fencing, we didn't actually need a fencing for this one side, so we've kind of left that out. All right, so we have our amount of fencing formula here, x plus 2y. And we know, based on the problem here, that that amount of fencing should be equal to 40. So let's throw that down into our problem here. So the amount of fencing is x plus 2y, and that should be equal to 40. So for these applied optimization problems, this is probably the hardest part, is figuring out what the equations actually are. So we have our objective equation, a equal to x times y, and then we have our constraint equation here, 40 is equal to x plus 2y. And so once we have these equations all settled, then it becomes like the optimization problems that we've already looked at. And so now we can actually just continue on with our normal routine. And so the first step of our kind of the more mathematical side of how we actually solve this problem is, once we have those two equations, then we're going to kind of start by solving our constraint equation for one of the variables. So it doesn't normally matter. Either one's fine, x or y. You want to pick the one that's easier. So it doesn't normally matter, but you want to make it easy on yourself. So look at the two variables and think about which one is going to be easier to solve for. So let's write down our constraint equation. 40 is equal to x plus 2y. So there it is. And, there's not too much of a difference, but I think this equation, it's a little bit easier to solve for x, because all I have to do is subtract 2y from both sides, and then I'm done. So I get x is equal to 40 minus 2y. If I had to solve for y, then I'd also have to divide by 2. It's just one extra step. Just makes it just a little bit more complicated. All right, so once we have solved our constraint equation for either x or y, then what we can do is we take this result and we're going to plug it in to our objective. So that's the next step here, is we're going to plug this in into our objective function. All right, so let's write down our objective function. It's a is equal to x times y. So it's our two-variable function here. Right now it's still in terms of both x and y. But we're going to take this result, this nice little formula we found for x, and we're going to plug it in wherever we see an x. So it's going to go in right there. And when we make that replacement, let's see what we get. So we're going to have the area is going to be 40 minus 2y, don't forget parentheses, times y. So I've replaced this x with 40 minus 2y. Now, we know eventually we're going to do some derivatives and set derivatives equal to 0 and try to solve for our variable here. So to help with that derivative process, right now we have a product of two variable terms. So to help with that derivative process, let's actually multiply this out. And when we do that, we get 40 times y minus 2y squared. So I'm just taking this y term and I'm distributing. All right, so we have our objective function. We have our objective function. And the nice thing about this version right here is that now we've gotten rid of one of the variables. And we're down to a one variable function. So that's kind of the key thing here, is we've used that constraint equation to kind of bring us back down to just a one variable function. And this is where the calculus happens. So now we just go through the regular motions. So that's the function we're going to try to optimize. All right, so step 3 is we're going to actually find our critical numbers. And the way we do this is by calculating the derivative. So we're going to calculate a prime of y. And then once we have that, then we're going to set our first derivative equal to 0, and we're going to solve that for, in this case, y. So our usual routine. All right, so let's get our first derivative. Our first derivative here is going to be a prime of y. And if we differentiate, derivative of that first term is going to be 40. And then the derivative of that second term is going to be negative 4y. So we end up with 40 minus 4y as our first derivative. Then we're going to set this equal to 0. And we're going to get an equation that we can actually solve for y. And so when we do this, we get y is equal to 10. And that's our critical number. Okay. Now, if our function is going to have a maximum, it's going to happen at this critical number. but we want to confirm that we do actually have a maximum. So that's where we're going to actually test or classify our critical number. So that's the next step of our work. And when we do this, we have a choice. We could do the first derivative test, which, wouldn't be too bad. We already have the first derivative. But I still think the second derivative test is a little bit quicker. So let's try that out. So as the name really suggests, we're going to need our second derivative. So let's calculate it. So let's get a double prime. We go back up to our first derivative. Derivative of that first term is going to be 0, and then the derivative of that second term is going to be -4. So our derivative ends up with, second derivative ends up being just -4. So it's a constant function. And the way the second derivative test works is we take our critical number, which in this case is y equals 10. We're going to plug that into our second derivative. And when we do that in this case, what do we end up with? Well, our second derivative is just a constant function. So no matter what I plug into this thing, I'm always going to get out -4. Okay, so when we plug in specifically 10, we get -4. And what that means is when our second derivative is negative, that means concave down. We draw our little concave down shape. And this kind of reminds us what the second derivative test tells. It looks like we have a high point, and that's precisely what the test actually tells us. So we have a local max at y equals 10. Now, we mentioned this in class last time, and what happens when we only have one critical number is we can actually say a little bit more. So there's only one critical number here. So not only is this a local max, it's actually the absolute max. A little more room. Yeah, one critical number means this is actually stronger. We have an absolute max at y equals 10. So our largest area is going to happen when y is equal to 10. All right, and we've basically done the heavy lifting here. And now all that's left to do is make sure we actually answer the question. This is kind of like the gotcha part. Just make sure you get everything in there that the question's asking for. So what were we trying to do ultimately? We wanted to find the dimensions that give us the largest area. So the thing that we were actually trying to look for here is the dimensions. So this is really telling us find x and y. Well, we found y. We need to get x. And this is where we can go back up to our first step, and we actually solve for what x actually is. We know x is equal to 40 minus 2y. So we're going to be able to figure out what x is. So in this case, we can use the constraint to find x. So x is equal to 40 minus 2y. We already had it nice and solved, all ready to go. And so all we're going to do is just plug in our y value that we found. So we'll plug in y equals 10. And when we do that, we get x is equal to 20. So I get 40 minus 20, which is 20. And we have both of our dimensions now. Y is equal to 10, x is equal to 20. And the only thing we want to be careful of is with these applied optimization problems is are any units specified? So we want to make sure our answer has the units. And so in this case, the way we're measuring distance, we're told right here, is in feet. So the dimensions for x and y should also be in terms of feet. So our dimensions, what we were actually after, x is equal to 20 feet and y is equal to 10 feet. And there's our answer, including units. So one of those little things, it's right at the end, but you want to make sure you actually answer the question. So find everything the question was asking you to find, and then if units are included, make sure you use the correct units. Now, just as a little aside, this is the correct, this answer should seem plausible, because if we go up to our diagram, x is the longer side. Why is x the longer side? Well, that makes sense because that's the one side that we didn't need to fence because our house was already there. So that it's going to make sense that this would be our longer side, and the other ones, those are going to be shorter because both of those are going to need fence, whereas only one side here would need the fencing. So it should kind of seem plausible that this is going to be our longer side because we're taking more advantage of the fact that our house is on the opposite side there. All right, so these applied optimization problems take a bit of work. And really the trickiest part, or at least what I think is the trickiest part, is not the calculus. The trickiest part is really kind of setting up your two equations that you're going to use. That tends to be the more difficult, developing the mathematical model. Once you have all the equations that you need, the calculus isn't too bad. All right, so we'll keep practicing this. So we'll try another example in class. So we'll see you then. Bye-bye.